nucleus, we will get that information. The other thing is that when we will have atoms which are similar to the hydrogen atom, for example, we are having helium plus. Now helium plus is having two protons here and one electron is going around. So the two protons I can treat with changing the number z here to 2, and then the electronic charge or the protonic charge. Similarly, lithium. Now lithium 2 plus is having 3 protons here, but again one electron is going around it, so we can extend the simple hydrogen atom assumptions to these atoms as well, these ions as well. That's the reason that we want to study the hydrogen atom. Now let me briefly tell about the story of the hydrogen atom, or the story of the atomic structure that started from J.J. Thomson to Rutherford. So let me start with the Rutherford model of an atom. So the Rutherford model of an atom was having some problems. The very first problem was of the emissions. Like electron is a charged particle, and if it is going around this nucleus, then we know that this is an accelerated motion, and in an accelerated motion, charged particles are supposed to radiate. And when this charged particle will be radiating all the way, then it will lose energy and it will spiral into the nucleus. While the observed thing was that the electron was not collapsing, but different kinds of emissions were there, and that's why this model couldn't explain this problem of the emissions or of the electron that will eventually fall into the nucleus. So the Rutherford model, it wasn't explaining those emissions, and when the emissions or emission spectrum, the emission spectrum of hydrogen atom was studied, and we got some series. For example, we got the Balmer series, we got the Paschen series, we got the Pond series, and so on. And they were suggesting some specific orbits and not the continuous or not the movement in any arbitrary path. So this was the reason that the Rutherford model failed here. So Bohr came up with a fantastic idea, and it was miraculous as well, because without any valid mathematics, it was supposed that the orbits around the nucleus in which the electron is orbiting are fixed, and he designated some principles to it. The very first one, so let me say that the Bohr model of hydrogen atom. So in this model, Bohr said that the electron orbits are stable. Electron orbits are stable, or we say that they are fixed, and the electron will lose energy or emit radiation or absorb radiation when it will jump from some higher orbit from some lower orbit. Means when it will jump from lower to higher, then it means it absorbs energy. When it will jump from higher to lower, it will emit energy, and some specific lines or specific emissions will be there which satisfied the series, the emission series which were observed. And how the electron will decide in which orbit it will have to move, this decision is to be based on the angular momentum of the electron. That when the angular momentum, when it will be an integral multiple of h bar, then we will say that, for example, mass of electron like mr cross p, so m, v and r, and this will be equal to n h bar, where n he called is the principal quantum number. It will be the positive integers only and not fractions of them. So the angular momentum, when an electron is in a given orbit, then its angular momentum will be for that orbit, and when the angular momentum will be different, it will go to another orbit, and there will be fixed values 1, 2, 3, and no orbiting in between, but some specific orbits will be there in which these electrons will go around the nucleus. Although there was no reason provided for this thing, that why? Because the why was not answered, but this assumption helped in explaining the emission of hydrogen. So the fixed orbits will be such that it will be, when the angular momentum will be h bar, then that orbit will be the first orbit. When it will be 2h bar, that will be the second orbit, and that all these orbits are spherical in nature. There was no reason provided for this, but this model worked very well for explaining the Balmer and the other series of the hydrogen atom. So the Balmer series, the Bond series, the Martian series, all those series were experimentally determined. Now some modifications occurred to the Bohr model. For example, the Sommerfeld model, the very first thing that it kept the principal quantum number n of the Bohr, but it added that the orbits, some of the orbits are spherical, but some are elliptical as well. And he added another quantum number L, and that was for the orbital quantum number. Means the orbits are not exactly spherical, but they may also be elliptical as well, like this. And he did some mathematics for it, and such that the L values, they range from 0 to n minus 1. And the shells means for a given L, for a given n value, we will call those as shells or orbits. And in a given n, there are then different values of L, which we will then call as subshells or orbitals. So this was one of the modification to the Bohr model, because different spectral lines were observed in the hydrogen atom, or in addition to those for the specific shell. Another modification that crossed the Bohr model was the observation of Zeeman effect. And Zeeman effect was that these lines, or these spectral lines, or the emission lines, they split. These emission lines split into two or more lines when we place the atom in a strong magnetic field. And to explain this thing, another quantum number was added, which was called ML, means the magnetic orbital quantum number, such that these MLs are ranging from -L to +L, including 0 with them. And this splitting was actually caused by the different orbitals, or the different motions of the electron under the magnetic field. But with a very high resolution, spectrometer, it was observed that the given spectral line, or the emission line from the hydrogen atom, it also splits into two. It is also splits in two lines, means every line, it was split it in two. It was just like composed of two very closed lines. For a normal spectrometer, it was like one line, but when it was observed with a high resolution spectrometer, then it was found that even in the absence of a magnetic field, a given line is composed of two different lines, and this was called the fine structure of the atom. Then another quantum number came in order to explain the fine structure of the hydrogen atom, and it was termed as MS, the magnetic spin quantum number. So spin was introduced there, and another quantum number came to solve the problem of the high resolution spectrometer, that why a given line is composed of two lines, and it was attributed to the spin of electron. Up to this, it was all the electron is a particle. And then a complete change occurred when de Broglie deviated from the previous models or the previous assumptions, and he said de Broglie waves are which we call the matter waves. Now, as in Bohr model, the Bohr assumed that the angular momentum will be integral in nature, but there was no reason provided to it. So de Broglie provided that reason, and he said that an orbit will be called a stable orbit if and only if the number of waves that are associated with the electron, means the electron waves, if they will be integral multiple of the orbit. So a given orbit will be stable only if it contained an integral number of wavelengths of the electron. For example, if I consider that this is an orbit, if this is an orbit, then in this orbit, if integral number of wavelengths are there, like 1 wavelength, 2 wavelength, 3 wavelengths, and so on, then it will be called a stable orbit. For example, this is the spherical orbit. So on a two-dimensional surface, I will have to mark it as a two-dimensional surface like a circle, and it is having somehow like this. So like this. Though my drawing is not that good in order to sketch this, but you can find very easily on the internet these diagrams. So it's something like this. So we will have like this. So here actually 3 wavelengths are there. This starts here, completes here 1, then 2, and then 3. So here we are having 3 wavelengths. If when the wavelengths, the number of integral wavelengths fits the length of that orbit, then we will say that it's a stable orbit, and the reason for that Y was given by de Broglie, and this was the first confirmation. This was the first confirmation that the electron, which was considered only a particle, it behaves like a wave at atomic level. So at atomic level, it behaves like a wave. And this electron will possess, means depending on its energy, is this is that E equal hc over lambda, or P equal h over lambda. So depending on, means from here I can write R cross P, the angular momentum, but depending on the wavelength, it will give us the energy of the electron. So a given energy electron will have a specific wavelength associated with it, and those wavelengths, when their integral multiple will fit a given orbit, then that orbit will be a specified or specific orbit. And he wrote that actually the thing which was written is MEVR is equal NH bar. Then this side, the angular momentum is from here, means h over lambda. So the number of wavelengths when they will fit means they will be integral multiple of h bar. And from here the quantum mechanics actually started. Quantum mechanics. Now, the Schrodinger wave equation is one of the first thing in the quantum mechanics, and to solve the Schrodinger wave equation for hydrogen atom, then the significance was that this equation was solved, means only mathematics was done without any assumptions like the Bohr, the Rutherford assumptions, the Bohr assumption or Sommerfeld assumption are the different modifications to the Bohr model. Here in quantum mechanics, we directly solve the mathematics without any assumption, and we came to know that for the first time the theory agreed with the experiments, and the theory was provided by the Schrodinger wave equation. So that's the reason that we solve the hydrogen atom in quantum mechanics in order to account for all the assumptions, means like principal quantum number here, then orbital quantum number here, then magnetic orbital quantum number here, finally the magnetic spin quantum number here. We will derive all these assumptions directly from the mathematical solution of the Schrodinger wave equation. So these are the reasons that the quantum mechanics played an important role in solving the problems of hydrogen atom. The different emission or absorption spectra are the splitting of lines, the story of the orbits and orbitals and the spin. They all can be solved with the help of quantum mechanics. So we will start with the solution of Schrodinger wave equation, the radial equation, and with the assumption of the hydrogen atom potential.